Hello once again, class, and welcome to another mock lecture. Today, we're going to be discussing polynomial inequalities, which are these four things. And I guess one might argue that this is also an inequality in the sense that it is literally the not equal to sign, but we're just going to focus on these four things. And we're going to start off by talking a little bit about the motivation. Why would anyone need to solve an inequality? Well, to answer that, let's consider a rocket ship that scientists maybe want to blast off into Earth's atmosphere. In order to get a spaceship up into space, that spaceship needs to overcome the force of gravity by reaching this thing that we call the escape velocity. So what scientists do is they set some complicated rocket science formula that has a ton of different variables in it, like thrust available and weight of the spaceship and all these different things. And what they do is they set that greater than or equal to the escape velocity of Earth, which is something like 11.2 kilometers per second, or like 40,000 miles an hour, or something like that, some crazy high number. So fundamentally, they have to solve an inequality to figure out what that thrust should be. Well, today we're not going to be doing any rocket science, but we are going to look at how to solve, I think I have 3 examples for us for how to solve polynomial inequalities. So let's take a look at some examples. All right, example number 1 says solve x cubed minus x squared minus 6x greater than 0. I'm trying to find where this is greater than 0. Which is basically asking us, hey, where is this polynomial function positive? Or another way to say that is, where is this polynomial above the x-axis? Because we're trying to look at when the y value is greater than 0. So that it's where the graph is above the x-axis. So we need to start by figuring out where this polynomial intersects the x-axis, and that's where the y value is going to change from being positive to negative or negative to positive. So one thing that we could do is we could graph this polynomial. And this is what it looks like. It looks like we have some zeros at -2, 0 itself, and also at 3. And we're looking in the spaces where the function is above the x-axis. So it looks like it's above the x-axis between -2 and 0, and also above the x-axis between 3 and positive infinity. And so that would actually just be the answer. It's part of the domain is your answer, right? It's the domain pieces where the graph is positive. Well, what if the question had asked us where it's greater than or equal to 0, right? How does this change the question? Well, now we're looking for where the function is above or on the x-axis. So we actually get to include these boundary numbers, as it were. And so the only thing that really changes is we have these square brackets that go around the numerical pieces, but the infinity keeps the open parentheses. So I think a natural question is, well, how do we do this without a calculator? What if we're not allowed to just graph this thing and kind of see what it looks like? What can we do? Well, the good news is we already know how to graph polynomials. We just need to know what the end behavior is, which if we're given the equation, we know. We need to know how to find its zeros, which again, we know how to do. Sometimes you have to use this thing called the rational zeros test, which in the way that I teach Math 111, we haven't necessarily gone over. But if you know what it is, then that is an option. Otherwise, at least one zero or a few zeros need to be given for us to be able to completely factor something. And then we also need to know how multiplicities affect the shape of the graph, right? So if we factor something and we find, oh, there's an even multiplicity, that means the graph is going to bounce and actually not change its sign. And what I mean by that is, if you have something that's positive and it bounces off the x-axis, it's staying positive, right? It's staying, and by positive, I mean like the actual y value is a positive value still, even after an x-intercept. But okay, we know about that, right? We know about those two things. So for example number 2, we're not going to just graph this thing on Desmos. We're not going to rely on technology. We're going to come up with the graph ourselves. So let's refresh how to do that real quick. First, we need to find the zeros. We need to find these x-intercepts. Now in inequalities, we call those things, very typically we call them boundary points. So we need to figure out where are the boundaries? Where's the graph potentially changing its sign from positive to negative or negative to positive? So fundamentally, that means we need to factor this. If we want to find the zeros of something, then we should look at how we can completely factor this thing. So first, I noticed that they all have a 3 and an x in common. All of these terms have a 3 and an x in common. So I went ahead and I pulled that out. And then now we can just focus on factoring this thing into x plus 5 and x minus 1, for which it actually does factor into. So there we go, right? There's our boundary points. Let's go ahead and plot those in there. The 0 is here, right? The -5 is here, and then we've got 1 right here. So those are our boundary points. Next, we need to talk about end behavior. And because there's a negative leading coefficient, we know that this thing rises to the left and falls to the right, so it's got to be doing this. It's got to have this kind of behavior. There are no multiplicities involved in this thing, and so at this point I would say, since we're just sketching, I don't really care about exactly where minimums and maximums are. We can go ahead and sketch a graph that'll look something like this. So remember, we're looking for where this graph, in this case, is below or on the x-axis. We're looking for where this function is less than 0. That means where in what regions of the graph is it below the x-axis down here. And so I highlighted those regions. It looks like the y values are negative between -5 and 0, and also between 1 and positive infinity. And because it's less than or equal to, we can actually include those values. So here's our solution. Oh my gosh, I just realized I made a critical error though. That should be a open parentheses, right? Infinity can't be a square bracket. The heck are you doing, Mark? All right, for example number 3, let's say we want to solve this one. Now, in this particular example, and it's a quartic function, we're looking for where it's greater than or equal to 0, but I'm not giving us anything. So if you know the rational zeros test, then you can actually do this. You find your p's and q's, you divide p by q, you test all of those things, and then you figure out, well, what are the zeros that you find? Since I don't do that in 2024 for my 111Z class, I'm going to have to give us some zeros. And in fact, I'm going to have to give us 2 of them so that we can figure out what the other 2 are with, at most, quadratic formula. So let's say that we know there exists, remember the backwards e means there exists, an x-intercept at x is equal to 2, with a multiplicity of 2, which means that that is a repeated 0. So I'm giving us a 0. Let's do the synthetic division once with 2, and then again with 2. And so this is what we get, right? We get x minus 2 is the first factor, x minus 2 is the second factor, so we might as well just consolidate those things to make that x minus 2 squared. And then we have -x squared plus 2x plus 6. And we're trying to figure out where that's greater than or equal to 0. You can't factor that traditionally, so you are going to have to use the quadratic formula. And by the way, another thing that I did real quick, because I know I'm going to use the quadratic formula, I always like to have my leading coefficient be positive. So I factored out a negative. If you'll notice, all of these signs just change and a negative shows up out in front. So here's the quadratic formula. Feel free to pause it. This video is not about the quadratic formula. I'm kind of assuming you guys know how to do that. But I end up getting 1 plus or minus the square root of 7 as the other 2 zeros, which means the other 2 factors are then x minus 1 plus square root 7 and x minus 1 minus square root 7. 1 plus square root of 7, by the way, is like 3.64-ish. And 1 minus the square root of 7 is like -1.64-ish. So when I plot these zeros, and you'll notice that I didn't include y values at all because, again, I don't really care about where the minimums and maximums are. I really just care about where this is above or below the x-axis. In this case, I don't think we've addressed this yet, but in this case, we're looking for where it is above the x-axis, or on. On is another one. So I went ahead and plotted my boundary points here. So this is about like -1.67. This is about 3.64. I think I said 1.67, but I meant -1.64 here. And then we got 2. So now we need to examine end behavior and multiplicities, right? We know there's a multiplicity at the x minus 2, so it's going to be rebounding, but I don't know if it's going to be rebounding like this right now, or if it's going to be rebounding like this. Right? To figure that out, we should talk about what the end behavior is. Well, it looks like it's a quartic function, and it's got a negative leading coefficient, so that means that it must be going down in both directions, and it has to bounce here. So I would say that it can't be like this, right? It has to be like this. And so then I'll just fill out kind of the rest of this thing, and it probably looks something like this. So now remember, we're looking for where this is above or on the x-axis, and that's all this stuff. And the cool thing is, like, you might be tempted to say, okay, well, it's 1 minus square root 7, right? That's what this value is, all the way up to 2, and also 2 to 1 plus square root 7, right? That's what that value is. And you'd be right. You can say that, but there's an easier way to do that. It's just everything between 1 minus square root 7 and 1 plus square root 7, because this is true, because we're allowed to be on the x-axis. That's why it's just this nice continuous interval from 1 minus square root 7 all the way to 1 plus square root 7. If it had just been this, well then yeah, now you have to do 1 minus square root 7 to union to 1 plus square root 7, right? But it's not that. It's stuff that's on, right, the x-axis, and so that is actually just going to be our solution. So it looks like this. All right, so that's it for this one. Just kind of 3 examples I wanted to go through for how to solve polynomial inequalities. The nice thing is that you can extend this idea to rational inequalities, to square root inequalities, to any kind of inequality that you want, right? You're just looking for where is it above the x-axis or below the x-axis, as long as it's set greater than or equal to or less than or whatever 0, right? Which you always can do because you can move things around in an inequality just like you can with an equality. Other than the fact that when you multiply by a negative, you have to flip it. But I'll probably address that at a different time. All right, so hopefully you guys learned something. If you have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.